Morning Year 11, so we're going to look at your multiple choice paper. So you'll see how well each question was done by looking at your spreadsheet. I've added the percentage of the class that got each question right, so you'll see relatively how difficult the questions were as you go through. So question 1 says, the tank shown has dimensions 5 by 4 by 4 metres. So the first thing I did before I even read the question was thought, okay, well if they're giving me that, I know that the volume is the product of all of those, so it's 80 metres cubed. I'm then told that the cube is filled with water, which has a density of 1,000 kilograms per metre cubed. So I have written the density equation, and then it asks for the mass of the water in the tank. So I've rearranged, and I know that mass is density multiplied by volume. So I multiply my density of 1,000 by the mass of 80, and I get 80,000 kilograms for question 1. So question 2, what is the best description of the meaning of the mass of an object? Well, it's not the space occupied by the object because that's the volume. It's not the force that gravity exerts on the object because that's the weight. It's not the closeness of the packing of the molecules in the object because that's to do with its density. Mass, remember, resists motion. So if you think about it, acceleration is force divided by mass. Okay, so acceleration, how much increase in speed you get, or change in movement really, is found by looking at how much force you need to move an amount of mass. And so it's the resistance of the object to changes in motion. Question 3 then. A student measures the dimensions of a cylindrical glass beaker. Sorry for knocking that. So it says, for which measurement should you use a micrometer screw gauge? So we've got one here. You can see that it measures to the nearest 0.01 millimetres. So a reminder on the scale, it's a good opportunity to do it on the video, that your top scale, when it wants to go in focus, maybe if I pop it down, your top scale measures millimetres, your scale underneath measures the next half along, and then your turning scale that you can twist round measures to the nearest 0.01 millimetres. So you can see that a micrometer is used to measure very small things. So it wouldn't be appropriate to measure the circumference or the diameter of a beaker. They're generally about 10 centimetres, aren't they? So for diameter, it's not going to be useful for those. The height of the beaker, again, not useful. So you're going for something that's very, very small, so the thickness. Question 4, I think, was the worst question on the entire paper in terms of how well you did with it. And then I looked at it and I'm not surprised because it is a tricky one. So a ball is thrown vertically upwards through the air. Air resistance does act on the ball. Which graph shows how its speed varies with time? So we're not even going to go to the graphs yet. We're just going to consider what we've got. So we've got a ball which we know will feel weight due to the gravitational field, but it's being thrown up, and so initially its velocity is upwards, and so it's going to be colliding with air particles above the ball, which will exert air resistance down. So originally the resultant force on the ball on the way up, we have the force is down. Okay, on the way back down we've still got the weight acting down, but this time it will be colliding with air particles that are underneath, and so the air resistance will now act in the other direction. Okay, so what we need to consider is how those forces affect the acceleration. Now, if it's being thrown vertically upwards through the air, hopefully you realise that it will start off with its maximum speed because of the force that it was thrown with, but as it travels upwards, it's going to decelerate because there's a resultant force down. Okay? And so we know that the speed will decrease to 0 on the way up. Okay? Because otherwise it would just continue upwards forever. But it reaches a highest point, and when it's at its highest point, the velocity is 0. Okay, so we can see that in all cases there's a point where the velocity reaches 0, so that's at its highest point. But we've said that the speed needs to decrease to 0, and we also know that as it slows down, the air resistance will be getting less, okay, because it's going to be colliding with less air particles per second. Okay, so the size of this air resistance force is actually going to be getting smaller and smaller and smaller. Okay, and so we know that that has an impact on the overall acceleration. Okay, we can write our equation. Acceleration is force divided by mass. Now, the mass of the ball doesn't change, it's just the ball. The force, however, on the way up is going to be the weight plus the air resistance. But we know that because it's slowing down, the air resistance gets smaller. So the total force acting on the ball as it travels upwards is actually going to decrease. Okay, so F decreases up until the highest point. So now let's have a think about what that means. If the force decreases, then so does the acceleration. Now let's come to our graphs. The gradient of each graph is speed divided by time, and so the gradient is the acceleration. And we've just said that on the way up, the force decreases, and therefore the acceleration decreases. And if the acceleration is the gradient, then the gradient also has to decrease. Okay, I'm using M for gradient. So you can see in part A, the gradient is constant, so we can write that off. Okay, we can see in B, if I grab my ruler, the tangent to the curve is actually getting steeper, so the gradient is getting steeper. So it's not B, because that would be acceleration increasing. Okay, so C and D are my only options now, because they both show the gradient getting less steep, so the acceleration is decreasing in both cases. Okay, so that allows us to narrow it down. Now let's think about what happens on the way back down. So the ball now is at its highest point, so we've reached this point on the graphs. We know in this case that we've still got the weight acting down, but this time we've got the air resistance acting up. So the air resistance now is opposing the weight. So overall the resultant force is going to be smaller. Okay, and so what we know then is that because the resultant force is now the weight minus the air resistance, and therefore it's a smaller value, the acceleration value isn't going to reach the same value that it did before. And as it falls, we know it will tend towards reaching terminal velocity. Okay, and we know that that will be when speed is constant. It's not going to continue to increase up. Okay, at the point where air resistance matches the weight downwards, we have no resultant force, and that would mean that there would be no resultant acceleration. And so the speed needs to tend towards being a constant, and that's what gives us D. Now that was a really difficult question. That was an A-star style question on the paper for sure. So let's have a look at question 5 then, a little bit easier. A cyclist rides 300 metres up a slope in 50 seconds. She then rides down the slope. Let's not forget that she's then travelling an extra 300 metres in 25 seconds. What is her average speed? Well, average speed is just total distance divided by the total time taken. Well, if she goes up and then back down the slope, her total distance is 600, and the total time is just the sum of 50 and 25. And when you put 600 over 75 into your calculator, or if you're very brainy and can do it in your head, you will get 8 metres per second. So 5 was much, much easier than 4. Okay, number 6 is a Hooke's law question. So we've got an extension load graph for a spring. The unstretched length of the spring is 17 centimetres. So before anything is hanging on it, we know that this is 17 centimetres. Now, before I've even read the question, I've written down Hooke's law, F equals kx. F is the force, K is the spring constant, and X is the extension. When an object is suspended from the spring, the length is 19.2. Okay, so we can say that when we hang this object, the extension is the difference between the original length and the final length. So the extension is 2.2 centimetres. So then we just look for 2.2 on the graph, and then we track down and we see that the load must have been 3 newtons. So that one was quite straightforward. Number 7, a cart has a mass of 10 kilograms. I've sketched it out. Always try and draw yourself diagrams so that you can visualise and not make mistakes. So a boy pushes a cart horizontally with a force of 50 newtons. I know that the cart accelerates with 0.5 metres per second squared. So I can work out the resultant force on the box, because resultant force, F, is equal to mass multiplied by acceleration, 10 times 0.5. So I know that overall, in order to be accelerated by 0.5 metres per second squared, the box must be feeling a resultant force of 5 newtons. If 50 newtons is pushing to the right, then I must have friction acting to the left in the opposite direction, so that when I find the difference between the two, I get 5. So the friction must be 45 newtons, so that the resultant is 5 newtons to the right. Number 8. A satellite orbits the Earth in an anti-clockwise direction at constant speed, as shown. It's a circular motion question. This one really is just a case of memory. We should remember that for circular motion, the force always acts towards the centre of the circle. Okay, and it's a simple fact if you just need to remember it. It's the kind of question that comes up quite repeatedly on exams, and it's always directed towards the centre of the turning circle. Doesn't matter where you are. If I'm over here, the force at this point will act inwards this way. If I'm here, the force will act upwards. It's always directed towards the centre. Number 9. An object is moving at 3 metres per second. A force acts on the object, so it will accelerate. After a time, the object is moving at minus 4 metres per second. The mass of the object is 5 kilograms. What is the change in momentum of the body? So, we're going to do final momentum minus the initial momentum is the change. Okay, now the final momentum is the mass multiplied by its final velocity. Its initial momentum is its mass multiplied by its initial velocity. So all I've done in purple is I factorised and said, well, that must be equal to m brackets v take u. It's important that you choose the numbers the right way round so that you get the right final direction. So the mass is just 5, the final velocity was minus 4, the initial velocity was 3. 5 times minus 7 gives us minus 35 kilogram meters per second. Number 10 is about gas pressure. So a piston traps a certain mass of gas inside a cylinder. Initially, the piston is halfway along the length of the cylinder. So it's here. The piston is now moved towards the open end of the cylinder, so it's moved this way, and the temperature of the gas remains constant. This bit is actually quite crucial. I forgot to highlight it last night. Okay, we know that if the temperature of a gas remains constant, then PV will also be constant. So that means pressure 1 in here multiplied by volume 1 in here must equal pressure 2 multiplied by volume 2. So it says, how are the density and the pressure of the gas affected by moving the piston? So we can see that the volume has increased. Okay, so V2 is bigger than V1. For these two things to remain constant, if the pressure, if the volume has gone up, which we can see it has, the pressure has to have gone down. Okay, so we know that we're looking for the pressure decreasing. The density, which is the mass divided by the volume, if you think about it, the mass of the gas has not changed. There's no more gas or less gas than there was before, but the volume is now larger. So if the volume is larger, you can hopefully see that the density also will decrease, and that gives us A. In 11, we've got a cement mixer sinking into a soft ground, but we place the cement mixer onto a large flat board. So the weight is the force that we can see through the cement mixer. The area that weight was acting through initially would have just been the bits of the wheel in contact with the ground, so you can hopefully see that would be a very small area. But by placing the board underneath, we're distributing that weight through a much larger surface area, and so the area here has gone up, the weight hasn't changed, and so the pressure has gone down. So the large area decreases the pressure on the ground. Okay, let's see if I can squeeze that. A builder in number 12 lifts 30 bricks from the ground onto a platform that is 2 meters high. Each brick has a mass of 4 kilograms. So it asks for the work done against gravity, so that's gravitational potential energy, by the builder in lifting the bricks onto the platform. So the work done is the energy transferred, it's mgh. So the total mass lifting all of the bricks is going to be 30 lots of 4. So that's m. G is always 10, and the height is 2. Plug that into the equation, and you get 2,400 joules. Okay, number 13. The power input into an electric motor is 400 watts. The efficiency of the motor is 85%. How much power is wasted? So we've got our efficiency equation, the useful power out compared to the total power in, multiplied by 100 is 85%. So let's just make a little bit more room so we can add this in. So we can say the useful power out over 400 is equal to 0.85 as a decimal. Okay, so therefore the useful power out is equal to 400 multiplied by 0.85. And when we pop that into our calculator, we get 340 watts. But the question asks for the wasted power. So if 400 went in and 340 of that was useful, then whatever is left must have been wasted, and that gives us 60. Okay, 14. Which energy resource does not derive its energy from the sun? Again, this is one just to remember. Hydroelectric power stations require water to be falling. Water is evaporated because of the sun, and then that falls as rain, which then falls down through the hydroelectric power station. So this does use the sun. Waves do require the sun. So tides and waves are to do with the gravitational pull from the moon and the sun. So waves will also be requiring the sun to exist. And wind is due to convection currents because of differences in temperature in the air, which also comes from the sun. Nuclear fission there is the only one that does not derive its energy from the sun. So 15. An object falls from a height of 5 meters. Air resistance can be ignored. And as it hits the ground, the object has 750 joules of kinetic energy. What is its mass? Well, the fact that air resistance can be ignored means that there won't be any energy wasted in the form of heat from friction from air resistance. So the potential energy at the top must be equal to the kinetic energy at the bottom because of the fact that air resistance can be ignored. So the 750 that they gain in kinetic energy, they must have had as potential energy at the top. So I can say 750 is equal to mgh. All I've done is I've rearranged. G is 10, h is 5 meters, and I get 15 kilograms. In 16, the graph shows the change in temperature of a substance as it's heated steadily, and you just have to identify when the substance is boiling. Okay, so when we are boiling, we're going from liquid to gas. And that happens without a change in temperature because the energy is being used to break the bonds in the liquid. Okay, so it can't be being used to increase the kinetic energy, which is going to increase the temperature. And so you can see I've labelled, we've got a solid heating up, increasing the molecule's kinetic energy. Then we've got bond breaking from solid to liquid in section B. Then we've got our liquid at this temperature, but now the liquid is increasing in temperature, and again now I see the second time where the temperature doesn't change, that will be liquid to gas, so that is boiling. 17 says, which statement describes a sensitive liquid in glass thermometer? Okay, so this is about definitions and remembering what sensitivity is. So sensitivity is how much change you get in your thermometer due to a change in temperature. And so a thermometer which gives a large increase in length for the same degree of temperature rise is sensitivity. You just need to memorise that. 18. A block of aluminium of mass 2 kilograms has an initial temperature of 20 degrees Celsius. It absorbs 7,300 joules of thermal energy, and specific heat capacity, which is C, is 913 joules per kilogram degree Celsius. So, specific heat capacity equation, Q equals mc delta T. I know that the total energy input was 7,300. The mass is 2, C is 913, and delta T is the temperature change. So I rearrange to get the temperature change, plug the numbers in, and I get 3.99 degrees Celsius. So that's the increase in temperature because it's temperature change, but it was already at 20 degrees Celsius. So the final temperature is the sum of the two. Okay, so I'm going to get 23.99 and two significant figures, that gives us C. Okay, in number 19 then, a metal rod is heated at end X. It's metal, so it's a solid, so we know that the particles are in a rigid lattice structure inside. Why does the end Y of the metal rod become hot? So we know that because it's a metal, it has free electrons. And we know that the heat source passes energy, so energy is transferred from heat to the kinetic energy of the atoms at side X. The electrons that pick up that energy are free to move throughout the metal, and so they travel, they've gained kinetic energy. They then collide with further particles and pass that energy on. Okay, so we've got the positive ions left behind because the electrons have moved on. They're vibrating, they're gaining kinetic energy because of the heat transfer in, but also we have the movement of the electrons and the collisions there. So that's just one to remember for conduction, for 19. Halfway then, 20. The table gives information about molecules. Which row describes a gas? So there are no bonds between gas molecules. They are completely free of one another. Negligible just means so small they don't exist, so no, 0. So we know that that's the case for a gas, and we also hopefully know that gas molecules are far apart. So that's chemistry as well as physics. I hope that most people got that one right. I think they did. So 21, a liquid at room temperature is put on a metal surface which is also at room temperature. A student blows gently across the liquid and its temperature decreases. What causes the liquid to become cooler? Okay, so we know it's at room temperature, so it's not boiling off, so it must be that evaporation is occurring. That's the first thing to notice. And so we know that in evaporation, which can happen at any temperature, the liquid on average is at room temperature, but within that, different molecules inside of the liquid will have different kinetic energy values. So on average they'll have a certain amount, but there'll be some with more and some with less. If the ones that have more energy happen to be at the surface of the liquid, they actually have enough energy to escape the liquid bonds, and they are then free to move off as a gas. And so the more energetic particles in the liquid escape into the air. So again, that's kind of a memory one about evaporation. 22, the sound from a loudspeaker must pass through two materials to reach a microphone. Which combination of materials gives the shortest time for the sound to reach the microphone? So the sound must be travelling fastest if it happens quickest. And we know that sound travels fastest in solids, and the only option where both materials are solid is C, so we choose C. Okay, and we know that the sound travels fastest because the particles are closer together, and sound is passed on through particle vibration. 23. Light travels at a speed of 2 × 10⁸ meters per second in a glass block, and the wavelength in glass for light is 4 × 10⁻⁷ meters. What is the frequency? So in this case, we just take our wave speed equation, we rearrange to get what we are trying to find. Frequency is wave speed divided by wavelength. I plug it in and I get 5 times 10 to the 14 hertz. 24. A tank contains water. Ripples are produced on the surface of the water. What causes the ripples to refract? Okay, so it's not about the temperature of the water. Let's just get rid of that one. The ripples hit the wall of the tank. That's going to cause reflection. And the ripples pass through a narrow gap. That's going to cause diffraction. The only option, by definition, is that refraction is where a wave changes speed as they move into a more or a less dense medium, and deep and shallow water causes water to change speed. So that's B. 25. The diagram shows a narrow beam of light incident on the glass air boundary. Some emerges along the surface of the glass and some is reflected back into the glass. Is this an example of total internal reflection? Well, no, because if it were total, the clue's in the name, all of the light would be reflected, and not all of it is. Some has travelled out along the boundary, so no. The fact is, the light that has refracted along the boundary, so the angle of refraction is 90 degrees, and so by definition, we must have reached the critical angle. Okay, so yes, we have reached that. 26. A thin converging lens has a focal length of 6 centimetres. So the focal length is further than the object. So the object has been placed closer to the lens than the focal point. An observer looks through the lens, which is placed 4 centimetres from the lens. Which description of the image is correct? So you can just remember that for a magnifying glass, the object is placed closer to the lens than the focal point. But I've sketched it on to help you. So you can see I've drawn 2 light rays coming off of the object, one passing straight through the centre of the lens. Now remember, our eye interprets that as having come from a straight line, so I've backtracked it. And again, this one's come in parallel to the principal axis, come out through the focal point, but again, our eye assumes that that ray has come from a straight line. And where those two intersect is where the image is found, and hopefully you can see that the image that I have got is much bigger, so it's enlarged, and it's virtual because these are not real light rays. So that gives us D. 27. Radiation from which part of the EM spectrum is used in the remote controller for a television? Again, this is a memory one, we're not going to spend a long time on this. Infrared is used in remote controls. 28. An isolated metal sphere is positively charged. It is then brought near to another isolated metal sphere that is neutral. What happens to the charges on the neutral sphere as it is as the positively charged sphere is brought close to it? So if this is neutral, it has to have an equal number of positives and negatives. Okay, so they will count in a paper 4, by the way. So whenever you're drawing this on, always make sure you've got the same number of positives and negatives. The positive charge comes from the nucleus, which is fixed, it's not going to move, so they don't change position. However, the electrons that are free to move are going to be attracted to the positively charged sphere, so they're going to get as close to this as possible, and they all move over. So the positive charges do not move, but negative charges move to the left. 29. Which statement about the resistance of a metal wire is correct? Well, we know that resistance inside of a wire is due to the fact that electrons collide with the positive ions, and that causes a bit of heat loss due to resistance. And so the longer the wire, the more likely there are going to be more collisions, and resistance goes up. The larger the cross-sectional area, the lower the resistance. Okay, again, you can just remember these proportionalities. The resistance is directly proportional to its length and inversely proportional to its cross-sectional area. So that gives you B. The diagram shows a circuit containing a cell in 30, 2 resistors, a switch and a voltmeter. When the switch is open, which is how we're seeing it, the voltmeter reads 1.5 volts. When the switch is closed, it reads 2 volts. What is the EMF? So let's look at how it is right now. So what we've got is a loop from the cell through the first resistor, the second resistor, and up. Okay, and the voltmeter then reads 1.5. When we then close the switch, we provide a different path. Okay, so electrons are going to come down here and they're going to take the path of least resistance, and effectively the wire has no resistance. And so the electrons are basically going to dodge this resistor and short circuit it out and all travel through here, which means they have all of the voltage that they picked up from the cell to spend over this resistor in this case. And so when the switch is closed, all of the voltage is dropped across this resistor, and therefore it takes the whole share, and so that must be what the battery can provide, so that's 2 volts. In 31, we've got diodes. Which circuit has a 0 reading on the ammeter? So we need to answer this question by knowing which side of the cell or the battery is positive and negative. So the longer side is positive, the shorter side is negative. So current flow goes from positive to negative, and we just need to see if the diode follows that. So in A, we can get through this diode, no problem. In B, we can also do that. In C, we can do that. And in D, we can get through the first one, but this one will block the current flow. Okay, so there will be no current in D. 32. A 4 ohm resistor and a 12 ohm resistor are connected in parallel. What is the effective resistance of this combination of resistors? So we've got 1 over R total is 1 over R1 plus 1 over R2 is equal to 1 over the first resistor 4 plus 1 over 12 the second resistor. That's equal to 3 over 12 plus 1 over 12. That's 4 over 12, but don't forget you flip it because it's equal to 1 over R total. So 12 over 4 gives us 3. 33. Why is a fuse used in an electrical circuit? So it's purely there because when the current is too high, it gets too hot and it melts and it breaks the circuit, and so it prevents large currents from flowing through the circuit, giving us B. 34. The diagram each shows a positive point charge. Which diagram represents the pattern due to the charge? So we know that an electric field line shows what would happen to a positive charge. Okay, so if we place a positive charge here, like charges repel, and so we're going to have a repulsive force trying to push it away. We're not going to have an attractive force. And we know that around a point charge we have a radial field, so that gives us A. 35. Beta decay. It's important to remember that beta is an electron, so it has a charge of -1, but no protons or neutrons. So we start with lead, 209, and we look to see, okay, so we definitely know it's an electron, so it's going to be either C or D, but we know that the total value on the top and the bottom needs to be the same on both sides. So 209 is equal to 209 plus 0, and 82 is equal to 83 minus 1, and that allows us to choose C. 36. Nuclear fusion is a reaction that takes place in the stars. You just need to remember which one is fusion and which one is fission. Fusion is where small elements join together, so the nuclei join to form a larger one. So hydrogen and helium in the sun fuse together. Energy is released. Okay, think about the fact that the sun is a star and the sun provides us energy. It has to be releasing the energy. So that gives us D. 37, we're almost there. The table compares the penetrating abilities, so how far it can travel and what it can travel through, and the ionizing effects of alpha and of gamma radiation. So alpha, which is a helium nucleus, is the least penetrating. It's stopped by a very thin piece of paper or a few centimetres of air. But it therefore is the most ionizing, because for it to have been stopped, it has to have had a lot of collisions with whatever it's travelling through. And during those collisions, electrons get knocked off of the atoms of the medium that it's travelling through, and that leaves those atoms ionised. So that's A. 38, an object is acted upon by a 3 Newton force and by a 4 Newton force. So in each diagram we've got the same setup. We've got the 4 and the 3 at right angles to each other, and they are all tail to tail. Okay, so the bottom of each vector is touching. So we know that when two vectors are tail to tail, to find the resultant of them we have to use the parallelogram method. So we have to draw construction lines at the end of each vector parallel to the other. So at the end of 4 we draw a construction line parallel to 3, and at the end of 3 we draw a construction line parallel to 4. And where those two construction lines meet is the end of the resultant, and we close from the tail to tail through to that point, and that gives us C. Almost there. 39 shows a uniform flat metal sheet. Uniform means that the density is the same everywhere, so the mass is equally distributed along. Flat metal sheet hanging freely from a nail at point A. One of the labelled points is at the centre of mass of the metal sheet. Now, it's not a perfectly symmetrical triangle, but what I want you to remember is that for an object that is perfectly symmetrical, what we do in order to find the centre of mass is to find the line of symmetry, and where those symmetry lines cross is where the centre of mass is. Now, this triangle is nearly perfectly symmetrical. It's not quite, but it's nearly there. So we know that it's going to be very close to being in the middle. It's not going to be at A. Okay, there's lots of mass underneath A, and B is still too high and D is too low. The centre of mass, so where all of the mass is thought to be acting from, will be at C. So you can see I've drawn what looks a bit like a line of symmetry. It's not a perfect triangle, but it's close enough. It would be that it would intersect. If I were to hang the nail here and it would spin round, the plumb line would hang vertically down again, and this bit here would be down at the bottom. Okay, so C. Last but not least, a heavy beam rests on 2 supports. The diagram shows 3 forces, F1, F2 and F3. The beam is in equilibrium. What is correct? You just need to remember the definition of equilibrium. It means no resultant force and no resulting turning effect. That's a definition you have to know off by heart, and it then gives you the answer C. And then we're done.